I'm back, and now we're going to finish up the practice problems from Chapter 6. Take a look at number 24 here. So, what it says is that one car has twice the mass of a second car, right? So we can kind of start out by saying, let's say that car 2 has twice the mass of car 1, but only half as much kinetic energy, right? So let's say that K2 is, I'll call it KE for kinetic energy, I guess. So we'll say that KE2, right, the kinetic energy of the second car, is equal to KE1 divided by 2. And this is the initial state, right? So let's say this is initial. And then in the final state, right, they're increasing their velocities by 8 meters per second. Then they have the same kinetic energy, right? So let's say that V1 final, right, that's going to be V1 plus 8 meters per second. And V2 final, that's also going to be, it's going to be V2 plus 8, where V1 and V2 are the initial speeds in the initial state. This is the final state. Okay, then they have the same kinetic energy. So basically, right, let's go through this, right? So we know that KE, the final kinetic energy of the first car, is going to be equal to the final kinetic energy of the second car. So this is going to be 1/2 m1 v1 final squared, right? Because 1/2 mv squared is the formula for kinetic energy. And this will be 1/2 m2 v2 final squared. And they want the original speeds of the two cars. Okay. So what we know, first of all, the 1/2s will cancel out. There's a half on both sides, so we can make life a little bit easier. So that m does not go away, just the half. So m1, like we set up here, is equal, let's work in terms of m2, I guess, right? Because m2 is 2 times m1, right? So this is 2 times m1. So we can rewrite this the following way. We can say this is m1 v1 final squared equals 2m1 v2 final squared. And now there's an m1 on both sides, so those will cancel. Let's get rid of that. Okay, so now we have this expression, right? So we can say, all right, I'll bring this over here. We've simplified this a bit. We can say that v1 final squared is equal to 2 v2 final squared. Okay. So that's one relationship that we can kind of, and so we can actually even expand this a little. Well, let's say, I don't want to do this, it's always a little tricky. Let's take the square root of both sides here. I think that'll make life a little easier. So we take the square root of this side, the square root of this side, and what we're going to get here is that v1 final is equal to v2 final times radical 2, right? Because this comes outside the square root as a perfect square, but 2 doesn't. Okay, so this is like one equation right here. I guess we could call this like equation 1. And actually, we could probably even make this a little more complex, right? Because what we could say here, because we know these are both the initials, so I'm not going to call that equation 1 yet, but we know that this is v initial plus 8, v1 initial plus 8, and this is v2 initial plus 8. So let's go ahead and put that in. So let me unbox this. So we're going to say, okay, v1 plus 8 equals v2 plus 8 times the square root of 2. Okay. So now, that's one equation, but we have two unknowns. Right? It's equation 1. So when we have two unknowns, v1 and v2, we have to have a second equation. So let's go ahead and we're going to use this information here. Right? Ke2 equals 1/2 Ke1. So 1/2 m2 v2 equals 1/2 of 1/2 m1 v1. Sorry, these are squared. So at least one of these halves will cancel out, right? That goes away. So now we get m2 v2 squared equals 1/2 m1 v1 squared. And now we know, like I said before, that M2 is twice, this is 2 times M1, right? So I can go ahead and say, all right, well, 2 M1, yeah, 2 M1 equals a half, sorry, 2 M1 V2 squared, sorry, equals a half M1 V1 squared. And so the M1s cancel. There's a lot of algebra here, as you can see. I can multiply both sides by 2, so I get 4V2 squared equals V1 squared. I take the square root of both sides, and now everything is a perfect square. So square root of that, square root of that. And what I'll get is that 2V2, right, equals V1. So that's, I'll call that equation 2. I'll bring that up here. So 2V2 equals V1. Right, that's equation 2. And now I could just do a substitution. I could take V1, take this, and sort of replace it right there. Right, so now I'll have something exclusively just in terms of one variable. So that's going to be 2V2 plus 8 equals V2 plus 8 times rad 2. What I'd want to do now is distribute the rad 2 on the right. So you get 2V2 plus 8 equals V2 rad 2 plus 8 rad 2. And I would, at this point, I mean, rad 2 is like basically like 1.4, I think 1.404, let's see. So square root of 2 is, yeah, it's 1.41, let's say. So this is 2V2 plus 8 equals 1.41 V2 plus, and I'll do that times 8. That's going to be 11.3. And now I'll bring everything with a V2 over to the left. So I will do this. I will minus 1.14 V2. Let's see what we got here. So it's going to be 2 minus 1.41, right, which is 0.59. So we'll have 0.59 V2. And then I'll bring the 8, I'll subtract 8 from both sides, right? So I get 3.3, and then I'll divide both sides by 0.59. Let me do that. So divide by 0.59, it cancels that out. Divide that by 0.59, so I get 3.3 divided by 0.59. And that gives me a grand total of about 5.6, so V2. And the initial V2 is 5.6 meters per second. Right, and V1 is twice that. So V1 is going to be 11.2 meters per second. Okay, so those are the initial velocities. So a decent amount of algebra. What is that one ranked? That's ranked a number 3. So number 3 is like whenever you see these number 3s, that generally indicates that it's a harder problem. I don't think this was too hard, but there's a lot of algebra, and I don't know, if you're not like super into physics, you might find this to be kind of like a pain in the rear. So, all right, next one, number 2, or number 38. Now this is a ranked 2, so it's not as hard. So we have a trampoline artist that's jumping upward from the top of a platform, so he's kind of doing like starting 2 meters high, he's going up like that. And they want to know, and his initial velocity is 4.5 meters per second. They want to know how fast is he going when he lands on the trampoline. So this is energy conservation, right? And the way energy conservation works is you can be like, all right, KE initial plus PE initial, that's the potential energy, equals KE final plus PE final. And what we're going to do here, for part A at least, is we're going to consider this here is the initial state, the initial position, and this is the final position. So now at the final, so what a good procedure to sort of move with these things is to figure out what, if anything, is actually 0 here, and nothing is 0 initially because it has initial kinetic energy because they say it leaves with the speed, and it has initial potential energy because it has gravitational potential energy, right? Because it's above ground. Ground is where is 0 is the 0 point, and just like with electricity, when you have a ground, when you talk about ground, that's the 0 voltage or the 0 electrical potential. In gravitation, ground is the 0 gravitational potential. In the final state, you are at ground, so this is 0 because you're at gravitational ground. You're at gravitational ground at that point. So basically, all of this initial potential kinetic energy plus potential energy is going to be converted to kinetic energy when he hits the ground, when he hits the trampoline, rather. So, okay, let's do what we got here. So this is going to be 1/2 mv initial squared plus mg y initial is the potential gravitational potential energy equals 1/2 mv final squared. Now the m's, even though you're given his mass, they do cancel out, so we don't have to bother with them. So those go away. And we're looking for v final, so we can we have numbers for everything here, so we can just solve for v final. If we do the algebra and kind of rearrange this, right, what it's going to end up being is this, v initial squared plus 2g y initial. Now y initial is 2 meters, right, because if we're calling the final position ground, then he starts at a y initial of 2 meters. So let's go ahead. It's really a plus or minus, right, when you do this. And in this case, it'll be minus because he's moving down. But let's just go through this. So they say v initial, I believe, is 4.5. Yeah, 4.5 meters per second. Right? Squared. Plus 2 times 9.8 meters per second squared times y initial, which is 2 meters. So I'm going to plug this into the calculator. So 4.5 squared plus 2 times 9.8 times another 2, square root that whole thing, you get about 7.7 meters per second. Do they say velocity or speed? How fast is he going? Well, if they ask for speed, it's 7.7. If they ask for velocity, it's negative 7.7. So now they're telling you the trampoline behaves like a spring, and they want to know how far does he depress it, right? So now what's going to happen is we're going to sort of redo this problem here. I'll do it over here. The initial, what was our final state becomes the initial state, and there's going to be some new final state. So the way it works is like this. So now we're going to say, okay, this is the initial state, right? When he hits here, that's initial. And then this thing, it's like a spring, right? So it's almost like there's like a spring, and this is going to depress a little bit. So this, maybe it depresses like to there when he hits it, and that's going to be the final state. So all of this kinetic energy is going to be converted to that, right? So the kinetic energy that he has is going to be equal to the potential energy stored in the spring, right? This is not gravitational potential energy. This is, so it's going to be 1/2, right, mv squared, and the formula for the potential energy in a spring is 1/2 kx squared. The halves cancel out. K is the spring constant, right, which you're given, is that 5.8 times 10 to the 4 newtons. It's basically an expression of how elastic the spring is. There's a half, so those go. And so if we go ahead and solve for x, if you do the algebra, and I'll sort of leave it to you to go ahead and do that, it's going to be the velocity divided by m over k. So this is going to be the 7.7 meters per second times the square root, and I think they said his mass is 62. So 62 kilograms over the spring constant, which is 5.8 times 10 to the 4 newtons per meter. It's a pretty big spring constant, so you're not going to see a very big depression here. It's going to be a small number, I think. And again, a big spring constant basically means you have to do a lot of, exert a very large force to move the spring from its equilibrium position, which is about 0.25, so about 25 centimeters. Right? So 0.25 meters, right? Or 25 centimeters. Okay, so that's that problem. I hope you found these useful, and if you have any questions, reach out to me.